Welcome to the video on displacement time and velocity time graphs. In this video, we're going to create a displacement time graph. And from the information in this graph, we're going to translate it into a velocity time graph. In part 2 of this video, we're going to use our displacement time and velocity time graphs to answer a series of 5 practice questions. In this first example, we're going to create a simple displacement versus time graph with time in seconds and displacement in meters. And we're going to translate this to its corresponding velocity time graph. And again, we'll have the time in seconds and we'll have the velocity in meters per second. Once these two graphs are complete, we're going to look at all the different quantities that we can extract from these graphs and how they compare, showing the true power of displacement time and velocity time graphs. Let's imagine a scenario in the classroom and your desk is located at a displacement of 0 meters. You're called to the front, to the teacher's desk, which is 2 meters in front of you, and you get there in 1 second. The teacher hands you an assignment to bring to your friend, so you pause there for 1 second while you're receiving the assignment. After that, you walk all the way to your friend's desk, which is 2 meters behind your desk, and you make it there in 4 seconds. You pause for 1 second, giving your friend the assignment, before scooting back to your desk in the next second, back at a displacement of 0. Let's just add a couple landmarks to this graph quickly so that we can reference it in the future. So your desk was at a displacement of 0, the teacher's desk was at a displacement of +2, and your friend's desk was a displacement of -2. To translate our displacement time graph into a velocity time graph, we're going to have to break our displacement time graph into segments so that we can analyze all the segments independently. So here we have our first segment where you walk to the teacher's desk, our second segment where you pause at the teacher's desk, our third segment where you walk past your own desk back to your friend's desk, our fourth segment where you pause at your friend's desk, and our fifth segment where you return to your desk. Next, we're going to calculate the slope of each of our individual segments. Now the slope is equal to the rise over the run on a graph. If we look at the units of a displacement time graph slope, we see that the rise is meters, the units is meters, and the run is a unit of second. So the units of our slope is meters per second. So this means when we calculate the slopes of our different segments, we're actually going to find the velocities that we're traveling in each different segment. In our first segment, we have a rise of +2 meters, +2 meters, and a run of +1 second. This means in our first segment, we're moving with a velocity of 2 meters per second in the positive direction. In our second segment here, we are standing at the teacher's desk and we're not moving. So our rise is 0 meters. And we stand there for 1 second. So we calculate a slope of 0 meters per second. This makes sense. We're standing at the teacher's desk, we have 0 velocity. In the third segment, the student moves from the teacher's desk, which is at a displacement of +2, to their friend's desk, which is at a displacement of -2. This is a rise of -4 meters from +2 to -2. So we have a rise of -4 meters. It takes the student 4 seconds to walk this displacement. So that's a run of 4 seconds, giving us a velocity of -1 meters per second. Let's pause briefly and discuss this negative sign. Displacement time graphs in physics have direction, which means the velocities that we calculate from them also have direction. In segment 3, the student moves from the front of the classroom to the back of the classroom. This is a negative direction, and therefore the velocity we calculate from this movement is also negative. One key thing to note in physics is the negative does not mean a lack of velocity, it just indicates the direction of the velocity, like the positives in segment 1. This just meant that you were moving in a positive direction. In the fourth segment, the student is again not moving. So the student has a rise of 0 meters, and they're standing still for 1 second, so we have a run of 1 second, giving the student a velocity of 0 meters per second. Again, this makes sense. We're standing at our friend's desk and we're not moving. In our final segment, segment 5, we're scooting back to our desk from our friend's desk. We have a rise of positive 2 meters from -2 to 0. And we have a run of 1 second, as it takes us 1 second to return to our desk. This gives us a final slope of 2, giving us a final velocity of 2 meters per second in the final segment. Now let's translate all of these velocities onto our velocity time graph. In the first segment, we move at 2 meters per second for 1 second. In the second segment, we're at the teacher's desk and we're not moving, so we have a velocity of 0 meters per second for 1 second. After that, we move at -1 meters per second for an entire 4 seconds. In the fourth segment, we again stop at our friend's desk and we move at 0 meters per second for 1 second. In our fifth and final segment, we're walking back to our desk and we move at 2 meters per second for 1 second. You've probably noticed that our velocity time graph is discontinuous. In our first segment, we're going 2 meters per second. In our second segment, we're going 0 meters per second. But we're never going any of the velocities in between 2 meters per second and 0 meters per second. This is because of our setup in our displacement time graph. In our first segment, we're going 2 meters per second. In our second segment, we're not moving. We never transition in our displacement time graph. If we were to transition, we'd just add a subtle curve here instead of a hard transition. And this would then also give us a subtle curve transitioning from 2 meters per second to 0 meters per second. For this example, that just makes things more complicated. So let's just assume that we can stop on a dime. For the next part of our analysis, we're going to calculate the areas between 0 meters per second and our different velocities. To make this a little easier, let's add a little emphasis on our 0 meters per second here and make sure we can still see our 2 previous 0 velocities. So the areas we're going to calculate is this area here between 0 meters per second and 2 meters per second, this area between 0 meters per second and -1 meters per second, and this area between 0 meters per second and 2 meters per second. As before, let's number these segments on our velocity time graph. So here we have segment 1, segment 2, segment 3 is our long segment here, segment 4, and segment 5. Each of these segments is a rectangle. So the next thing we're going to do is calculate the areas of these rectangles. The area of a rectangle is equal to length times width. For the purpose of our example, let's assume the height is the length and the width is the base of our rectangle. Calculating the area of our first rectangle, our first segment here, we have a length of 2 meters per second. And we have a width of 1 second. As I stated before, the units are the key to physics, especially when we're analyzing graphs. So let's keep our units through this area calculation. So we have a length of 2 meters per second in our first segment and a width of 1 second. 2 multiplied by 1 is 2. The units on the top and the bottom cancel. So our seconds on the bottom cancel with our seconds on the top because anything divided by itself is 1. So we're left with 2 meters. Before we more deeply analyze the area of our first segment, let's quickly calculate the areas of our remaining 4 segments. So our second segment actually has no area because the length is 0 and the width is 1. So we have a length of 0 meters per second, and we have a width of 1 second. This gives us an area of 0 meters. In our third segment, our third rectangle, we have a length of -1 meters per second. -1 meters per second, And we have a width of 4 seconds. -1 times 4 is -4. Our seconds cancel, -4 meters. In our fourth segment, we again have no area. So our fourth segment has a length of 0 meters per second, and it has a width of 1 second. This gives us an area of 0 meters. Our fifth and final segment has a length of +2 meters per second. +2 meters per second, and it has a width of 1 second. 1 second. Our seconds on the bottom cancel with our seconds on the top, and we're left with an area of 2 meters. Let's take a moment now to pause and look back at everything we've done before I tie it all together and then ask you some probing questions to see how well you've understood the content. So we started by creating a displacement time graph using the displacements of a student moving around a classroom. From these displacements, we then calculated the slopes of different segments, which gave us the velocity and direction of which the student was moving. We then used these velocities to create a velocity time graph. When we finished our velocity time graph, we entrapped the area between the velocity that our student was moving and 0 meters per second and calculated all of these areas. Now, for the next part of the analysis, let me just move everything we calculated to the sides of the page so we can tie it all together. I want to place emphasis on the units and their importance one last time, because they truly are the key to bringing everything together. You've probably already guessed what these areas represent. These areas represent the original displacements in our displacement time graph. The first area had a displacement of 2 meters. This was our student moving 2 meters forwards to our teacher's desk. The second area had a displacement of 0 meters when our student stood at the teacher's desk. Our third area had a displacement of -4 meters. This was the student walking back to the friend's desk. The fourth area had a displacement of 0 meters when the student was standing at their friend's desk, and the fifth area had a displacement of 2 meters, and this was the student returning to their own desk. So a displacement time graph doesn't just show you your displacement, it also shows you your velocity and the direction you're moving. As well, a velocity time graph doesn't just show you the velocity you're going at different times. From a velocity time graph, you can also calculate your displacements. Please join me for part 2 of this video, where we'll take the 2 graphs we created in part 1 and answer 5 commonly asked test and quizzes questions on displacement time and velocity time graphs. Thank you for watching the video on displacement time and velocity time graphs.